Hi everyone. So let us discuss the type of voids present in a particular unit cell, and with the type of voids we will also see the position of those voids in a unit cell. So we know that if we want to describe the properties of an unknown crystalline solid, we define a 3D space, a small space which we call a unit cell, which when repeated in 3D gives you a particular type of lattice, and which on further repeating gives you the entire crystal. Now, in order to study a unit cell, we need to know the arrangement of atoms in a particular unit cell, and also the type of voids present in those unit cell, and also their positions. So let us see the type of voids and also their position. So we know that if we see the arrangement, and voids in 3D, then arrangement we are not discussing today. We will discuss the voids. So you know that in order to have a 3D arrangement of atoms, we start from 1D, where we say then an array of atoms is aligned along a particular axis. Then we have 2D. In 2D we discuss the square close packing and hexagonal close packing 2D, and from that we come to 3D using those SCP-2D and HCP-2D. So when I say 3D, we study simple cubic unit cell, which we also call primitive unit cell. Then we have BCC, FCC, and we also have H-centered, N-centered. So let us see the first unit cell, that is simple cubic. Now in simple cubic, if I talk about the arrangement of atoms, then we know that it's a primitive unit cell where the atoms are arranged, or they are present at the corner, only at the corners of the cube. Now, so since they are present at the corner of the cube, you know that the Z value, that is the number of atoms present in this particular unit cell. Now this number of atoms has also incorporated the contribution of a particular atom. So Z comes out to be, that is 8 at the corners, and the contribution by each is 1 by 8, because you know that an atom at the corner is shared in 8 cubes. So this is your 1. Now if I talk about the type of void, then it's simple that it is having a cubical void. So what is the type of void? It's a cubical void. Because you know the entire space inside the cube is empty. So that is basically a cubical void. Now when it comes to BCC, that is body centered cubic unit cell. But if I talk about BCC, you know the Z value is, that is 8 at the corners multiplied by its contribution plus 1 at the body centered, and you know that it is completely inside, so I multiply by 1, so it comes out to be 2. Now BCC, what is important to understand is that in SC we know, in the simple cubic we know that the atoms at the corners, they are touching each other along the edge, but in BCC they are not touching each other along the edge. In fact, they are touching each other along the body diagonal. So we do not actually talk about void in BCC. It is basically what you can say a distorted octahedral kind of void. So if we do not define it, so not defined, it's basically, you can say, a distorted octahedral kind of void. Now when it comes to FCC, unit cell, or to be precise we can call it CCP arrangement, FCC unit cell and CCP arrangement, we know the Z value comes out to be, we have 8 at the corners multiplied by its contribution, plus we have 6 face centers, and the contribution is half, so it comes out to be 4. Now we know that FCC is basically, now when I talk about FCC, we discuss 2 kinds of voids, that is tetrahedral void and the octahedral void. So FCC and CCP, tetrahedral and because you know that FCC and HCP 3D for that matter is basically we get it from the HCP 2D. So we have two we know that HCP 2D is having a triangular void, right? So from that we come to FCC and we form FCC and HCP 3D. So here we talk about tetrahedral and octahedral voids. So let us see the type of voids. We have already seen it is tetrahedral and octahedral. And what is important is to understand the number of those voids and also their positions. So let us see. So suppose this is a cube. Now this is a cube. If I choose the atoms, like if I choose the atoms at the face centers, like for example, if I choose the atom here, 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 if I choose these atoms at the face centers, if I choose the atoms at the face center, and if I join the atoms at the face center, this is basically my first octahedral void. This is my first octahedral void which is present at the center, body center. Now, we need to understand that if I join these 6 face centers, what I get is the octahedral void. So this is my first kind of octahedral void. Now let us see, can we have another type of octahedral void? Now, if I see this cube only, what I am doing is just extend it. Just extend it. Now, what I am doing is I am choosing the 2 face centers, basically 4 face centers. 2 face centers of the adjacent cubes, 2 face centers of this particular cube, to change the color of the pen, 2 face centers of the same cube, 2 face centers of the adjacent cube, and these 2 corner atoms. These 2 corner atoms. What I'll see is that I get another kind of octahedral void, and this time it is present at the edge center. So this time this is present at the edge center. Edge center. So we have got 2 types of octahedral voids. One is the body center, at body center, and the second one is at edge center. So if I want to know the exact number of octahedral voids in an FCC unit cell, what I'll do is, now let us see the number of octahedral voids. So positions we have already known. Now we already know the positions, that it is at the body center and also at the edge center. So if I talk about the number, how many octahedral voids are there? So basically we have 12 edges in a cube, and you know the contribution by the atom at the edge center is basically 1/4. That is, it is divided in 4 cubes. So we have 12 edges multiplied by 1/4, and one is present at the body center, and it is completely inside, you know, so it is 1 into 1. So what it is 3 plus 1, that is 4 octahedral voids. Now we have 4 octahedral voids in a FCC unit cell. One kind of octahedral voids are present at the edge centers, the other is present at the body center. Now next thing is, what if I want to know the distance of this octahedral void from the cornermost atom? So basically what I want to know is the distance of distance. This is my cornermost atom, and we know that this is your body diagonal, and here I have the octahedral void. So I want to know this distance. Now this is exactly half of the body diagonal. We know that the body diagonal is equal to root 3a, and I want to know this distance. This is exactly half of it. So if I want to know the distance of octahedral void from cornermost atom, this is equal to root 3a by 2. So now we know one kind of void, that is octahedral void in FCC. Now let us see the other type of void, that is tetrahedral void, their number and their position. So if I draw the cube again, or let us discuss it here only. Okay, let us see. Now, for tetrahedral voids, what I am doing is, I am choosing this cornermost atom, and I am choosing 3 atoms at the face centers, adjacent face centers. You know that this cornermost atom is touching the face, the atoms at the face centers. Now, and this one. So, this is like this. This is my, now, you know that this is your body diagonal, this is your body diagonal. So one tetrahedral void is here, that is at the body diagonal. At the body diagonal. Now, other kind of tetrahedral void is, if I can form the triangle here as well, this triangle, equilateral triangle, and here. Other tetrahedral void is here. This is also at the body diagonal. This is also at the body diagonal. Now, if you see carefully, so if I want to know the number of tetrahedral voids, that is equal to, first of all, how many body diagonals are there? There are 4 body diagonals in a cube. Now, and on one body diagonal, I have 2 tetrahedral voids. So this is my one body diagonal. At one body diagonal, I have 2 tetrahedral voids. So basically, this comes out to be 4 into 1 plus 4 into 1, because total are 4. So this comes out to be 8. So my total number of tetrahedral voids are 8. Again, if I want to know the distance, this distance of tetrahedral void from the cornermost atom. Now this body diagonal is basically divided into 4. These are the cornermost atom. Here is a tetrahedral void. Here is a tetrahedral void. This is the body center. So you know that this distance is root 3a by 2. Then this distance comes out to be root 3a by 4. So basically the distance of a tetrahedral void from the cornermost atom is root 3a by 4. Now, next thing is, so these are the tetrahedral voids. Now I come to a conclusion that for a unit cell, having both kind of voids, having tetrahedral and octahedral voids, this formula is only valid for those unit cells which are having both kind of voids. So if Z is for say n, the number of atoms is n, then the octahedral voids comes out to equals to this number, and tetrahedral voids is basically twice of this number. So if a unit cell is having n as the number of atoms present in that particular unit cell, then octahedral voids is equivalent to n, and tetrahedral voids is equal to twice of n. Now, so we have already seen in the case of FCC. Now, same thing goes for HCP. If I talk about HCP 3D, that is hexagonal close packing 3D, which is again formed using HCP2D as a base. So what I get is, we know that Z comes out to be 6. The Z is 6 in HCP. Now, the Z comes out to be 6. So if I want to know the octahedral voids, the octahedral voids are equal to 6 only, because 2 equals to this number, and tetrahedral voids are basically 2 into 6, that is 2. So in a HCP 3D, I have 6 octahedral voids and 12 tetrahedral voids. So this is how we have seen the type of voids present in the unit cells, after the arrangement of atoms in those unit cell, their positions and their number. I hope you have understood the thing. Now in the next class, we will see the arrangement of atoms, and more importantly, we will see the parameters. We will see the number of atoms, we will see the packing efficiency, we will see the relation between A and R, which is very important, and we'll see the coordination number, the examples. So I hope you have understood it. Thank you so very much. Do take care.